Welcome to Ask and Learn.
In this problem, we have a cylinder that initially contains argon gas at a specified state. The gas is stirred while being heated and expanding isothermally. We need to calculate the amount of heat transfer. So we assume the cylinder is stationary and thus kinetic and potential energy changes are zero. We also assume that the air is an ideal gas with constant specific heats. And the compression or expansion process is quasi-equilibrium. Now, the contents of the cylinder form a closed system, since no mass enters or leaves. So the energy balance equation can be written as the energy in minus the energy out is equal to the change in energy of the system delta E. So from this equation, we can expand it as follows. The energy into the system is due to heat, so that's Q, plus the work done by the paddle wheel. And that's minus the boundary work out of the system. And then this is equal to the change in internal energy of the system, delta U. So delta U can be written as M into U2 minus U1, the specific internal energy per unit mass. And we can write this further as mCV times a change in temperature T2 minus T1. But remember that for an isothermal process, T2 is equal to T1. So this right-hand side goes to 0. Now, since the right-hand side goes to 0, and U is a function of temperature for ideal gases, we get that the internal energy U2 is equal to the internal energy U1. So the two states have the same internal energy when the temperature of state 2 is the same as the temperature in state 1. So what this tells us, if we look at the energy balance equation, is that the heat transfer into the system, Q in, is equal to the boundary work out of the system minus the work done by the paddle wheel into the system. And hence we get the heat transfer into the system to be the value for the boundary work given as 15 kilojoules minus the work done by the paddle wheel, which is also given to be 3 kilojoules. And so the heat transfer is 12 kilojoules into the system.